Gnanam paramam dheyam. Knowledge is supreme.
Friends, in the last lecture, we looked at what is residence time distribution and what is non-ideal reactors, and we initiated discussion on what are the experimental methods to measure the non-ideal situation inside a reactor. So, let us look at a little bit more into it. So, the method to do that is basically to inject a tracer. We need to inject a tracer into the reactor, and let us say at time t equal to 0, a certain concentration of tracer is actually injected into the reactor, and then the effluent concentration, the tracer concentration in the effluent is measured. So, now if we measure the tracer concentration in the effluent, then this gives an idea about the non-ideal behavior of the reactor. Now, in order for this to conduct such an experiment and to measure the tracer concentration, the tracer has to possess a certain properties, and the tracer must be non-reactive. Otherwise, the tracer is not going to reflect the true non-ideal behavior, because some amount of tracer which is actually injected into the reactor is now going to be consumed in some reaction, and it should be easily detectable the experimental methods that are available, the measurement techniques that are available should be sensitive enough to detect the tracer concentration, even small amounts of tracer concentration in the effluent stream. And then the properties of the effluent must be similar to that of the reaction mixture. So, the properties must be similar to that of the reaction mixture, otherwise it reflects a different behavior. So, in order to capture the non-ideal behavior of the reactor, the properties must be similar, for example, viscosity, etc. And then it has to be completely soluble in the reaction mixture, and it should not adsorb onto the reactor walls, otherwise some of the tracer is actually consumed, and so it does not reflect the non-ideal behavior completely. So, now the question is, how do we measure the residence time distribution? So, there are two injection methods . There are two methods which are commonly used, which is in order to detect the residence time distribution, which is a reflection of the non-ideal behavior of the reactor, and the two methods are the pulse input method and the step input method. These are the two methods that are used experimentally to measure the residence time distribution. So, let us look at a little bit more deeply into the pulse input method, and later we look into the step input method as to what these two different methods are and what are the purpose of these two methods. So, let us look at the pulse input method. So, now suppose we consider a single input single output system. Suppose we consider a single input single output system, that is, suppose if there is a reactor Suppose if there is a reactor and then there is a single input stream to the reactor and single output stream to the from the reactor, and suppose if there is a feed stream, there is a feed stream which is present here, and let us say that we put we inject the tracer, along with the feed which actually goes into the reactor, and maybe the total concentration of the tracer is N naught, and it has to be a pulse tracer. So, we will describe in a short while what is meant by a pulse tracer injection, and then suppose there is an effluent stream, and then we can actually detect the concentration of the tracer in the effluent. So, this is a reactor and it has a single input and a single output system. So, now the tracer that is injected has to be a pulse at a certain time. So, let us say at time t equal to 0, we inject a pulse of tracer, that is a certain concentration of the tracer in as short time as possible, it is actually injected into the reactor. So, that is what is called as a pulse input. So, suppose if this is the concentration of the tracer and this is minus tau, some time before and some time later. So, there is some time before the injection point, there is no tracer in the reactor, and some time later also there is no tracer in the feed. So, just give a short pulse and then leave it. Now, once we do this, if we monitor the concentration of the tracer in the effluent stream of the reactor, then the kind of concentration profile that one will expect is basically, it looks like this. So, this is time and this is the concentration of the tracer as a function of time. So, this kind of a curve is what is called as a C curve in residence time literature. So, the concentration of the tracer as a function of time is what is called as the C curve. So, now suppose if we know, if such is a system, question is how do we find this concentration curve. So, how do we find this? We need to find the C curve, and how do we find the C curve? So, we have to make some assumptions. So, if we assume that the only fluid flow through the reactor is the only one which is actually carrying the tracer, and if we assume, which means that there is no dispersion between the point of injection and the entrance of the reactor. And later in one of the lectures, we will actually account for the presence of dispersion in the reactor. Suppose if we assume that there is no dispersion, and then we measure the concentration of this tracer at the exit, that is the effluent stream. Now, the trick to measure the concentration or to construct the C curve is basically to choose a very small time step delta t, and the delta t should be chosen such that the concentration of the tracer in the effluent stream within this delta t does not change significantly, and then measure the concentration of the tracer at every delta t which is very, very small. So, measure the concentration. So, choose sufficiently small delta t and then measure the concentration C of t. Now, once we measure this concentration, and suppose if V is the volumetric flow rate of the effluent stream, and the volume of fluid that actually is leaving the reactor in the time delta t, volume in time delta t. So, leaving in time delta t. So, volume of the fluid leaving in time delta t should be equal to the volumetric flow rate at the effluent stream multiplied by the corresponding delta t. So, therefore, the amount of tracer that is actually leaving the effluent stream in time delta t, that is given by the concentration of the tracer in the effluent stream at that time multiplied by the volumetric flow rate V multiplied by delta T. So, that gives the total amount of tracer that actually leaves in this time delta T. Now, what does this mean? So, this is the amount of material, this is basically the amount of material, amount of tracer that spent an amount of time between T and T plus delta T. So, what this means is that this is the amount of tracer which has actually spent the amount of time between T and T plus delta T. So, that is the total amount of tracer in that times that has actually spent that much time inside the reactor. So, now if N naught, which is the total injected as we observed in the schematic before, if N naught is the total injected, total tracer. So, that is the total amount of tracer which is actually injected into the vessel. Then delta N by N naught is nothing but the fraction that has residence time. So, remember residence time is the time spent by the material inside the reactor, whose residence time is somewhere between T and T plus delta T. So, the time that certain amount of material has spent inside the reactor, if that is between T and T plus delta T, and that will be the fraction of, that will be the material which is going to come out of the vessel in that time delta T, and therefore, the fraction that has residence time between T and T plus delta T is simply given by delta N divided by N naught, and that is equal to C, which is the concentration of the tracer in the effluent, multiplied by the volumetric flow rate of the effluent stream into delta T, which is not, this whole numerator is nothing but delta N divided by N naught. Now, suppose for pulse injection, if we define an RTD function, E of t, which is basically given by V into C of t divided by N naught. So, that is the definition. So, that is the concentration of the tracer in the effluent stream multiplied by the corresponding volumetric flow rate divided by N naught. So, that is the amount of that is the if we define that as the RTD function, then we can write the fraction that has the residence time between T and delta T as delta N by N naught, that is equal to E of t into dt. So, what does this E of t represent? E of t is the RTD function, which is V into C t divided by N naught. What it represents is, it basically describes how much time different fluids elements have actually spent in the reactor. So, this quantity E of t, which is the residence time distribution function, it quantifies or describes how much time different fluid elements have actually spent or have resided inside the reactor before they leave the reactor. So, that is an important property of the vessel of the reactor, which is actually captured in this residence time distribution function. So, what can we do with this? So, if E of t is basically describes the amount of material that is actually residing in the reactor, then E of t dt is basically, so this quantity, it represents the fraction of fluid entering the reactor that has spent time between T and T plus delta T. So, it is very important to understand this function E of t times dt, that is the fraction of the fluid, that is basically delta n by n naught, which is basically the fraction of fluid, total fluid that enters the reactor and has spent time between t and t plus delta t. So, suppose if the total amount of tracer that is actually fed into the vessel n naught, if that is not known, suppose if it is unknown, which may be the case in many situations. If that is unknown, then the amount of n naught can actually be detected from the effluent stream. It can be detected or calculated from the effluent stream concentration, from the concentration in the concentration of the tracer in the effluent stream. So, how do we do this? So, dN is essentially given by the volumetric flow rate V multiplied by C of t into dt. So, therefore, N naught, which is the total amount of tracer that is actually fed into the reactor. Remember, it is a pulse tracer, that means there is a sudden injection of the tracer at a certain time and very short time, and therefore, the total amount of tracer that actually leaves the reactor from 0 time to infinite time should be equal to the total amount of tracer that has actually been fed into the reactor as a pulse. So, therefore, the N naught will be 0 to infinity multiplied by V into C of t into dt. So, that is the total amount of tracer that has actually been fed into the reactor. Suppose if we assume that the effluent stream volumetric flow rate is constant, suppose if we assume that the effluent stream volumetric flow rate is constant, then N naught, which is the total amount of tracer that has been fed inside, is given by V naught into integral 0 to infinity C of t into dt. So, therefore, the residence time distribution function E of t, that is given by V into C t divided by N naught, and that is given by V naught, because the effluent stream volumetric flow rate is maintained constant. We assume that it is constant, divided by V naught into integral 0 to infinity C of t dt. Okay. So, from here we can easily see that the residence time distribution function E t is essentially given by the concentration of the tracer at any time divided by the total amount of tracer that is actually leaving the reactor, or the total amount of tracer that is actually entering the reactor. So, if I plot this function, so suppose the concentration versus time graph. So, the effluent concentration as a function of time, if it looks like, suppose if it is a bell shaped curve, suppose if it is a bell shaped curve. So, that is the concentration of the tracer in the effluent stream as a function of time. Then the area under this curve, so this area under this curve is essentially N naught, which is the integral 0 to infinity V into C of t dt. So, a weighted area under this curve essentially gives the total amount of tracer that has actually been fed into the reactor. So, now if I plot the corresponding residence time distribution function, so E of t, then the curve essentially looks like this, and this is so if we know what is the C t versus or the C curve. So, this is the C curve. So, if the C curve is known, then we can actually find out the E curve. But in order to find out the E curve from C curve, we need to be able to integrate the expression or find the area under the C curve. Only if we are able to find the area under the C curve, we will be able to construct the residence time distribution function. So, now from this we can actually find out what is the fraction of material which is that is leaving the reactor with a specified residence time, specified range of residence time. So, suppose if I want to know what is the fraction of material leaving with residence time between T1 and T2. So, I want to know what is the fraction of the material which has been fed into the reactor and that has spent the residence time, that has spent sufficient time, but the time that it has spent is between T1 and T2, certain time T1 and T2. So, that fraction is essentially given by integral T1 to T2 E of t dt. So, if we know the residence time distribution, then there are a lot of properties or a lot of information about the reactor can actually be extracted from the RTD function. Now, suppose if I want to know what is the fraction that leaves the reactor with residence time from time t equal to 0 all the way to infinity, which means what is the amount of material which leaves the reactor with residence time in the whole spectrum of time. So, that will simply be given by for 0 less than t less than or equal to infinity, that fraction will simply be 0 to infinity E of t dt, and that is equal to 1. Which means the area under the RTD function curve is 1, which is true because it is a fraction, and so the area under the curve should be equal to 1. Now, the question is how good is this pulse input method? Can it be used in all situations in order to find out the residence time distribution function? And that is really not the case. There are certain limitations. So, the limitations are, there are certain limitations. So, it is important to obtain a reasonable pulse as the input. So, that is often not very easy to do. So, it is very difficult to get reasonable pulse as input. Why is that? Because the injection has to be done at a very short period, and a sufficient quantity of the tracer has to be injected in this very short period. So, that is not a very easy task, and it is not very easy to perform such an experiment where the tracer is actually injected into the stream in a very short time and sufficient quantity. So, injection has to be in a very short time. It has to be in a very short time span, and more importantly, the reactor must have negligible amount of dispersion between the point of injection and the entrance of the reactor, over which very limited control can actually be established on the reactor. One cannot control the extent of dispersion. So, if the reactor has reasonable dispersion, then this pulse input method simply does not provide a clean way to find the residence time distribution. However, pulse input method is basically, it is a very simple and direct method, provided these three conditions are actually satisfied. Now, another important caveat associated with the pulse input method is that if I look at the concentration curve, in certain situations there can be a very long tail which is present in the C curve. So, this is the C curve. So, now the concentration curve has to be integrated. Remember that E of t is basically given by C t divided by integral 0 to infinity C t dt, provided that the effluent volumetric flow rate is constant, there is no dispersion, etc. So, in order to perform such an integration, one needs to do a numerical integration of this curve, this C curve, and if the tail is very long, then it is not easy to integrate this expression numerically, and it can actually cause inaccuracies in the integral. So, therefore, the long tails can actually lead to inaccuracies in estimating this. Long tail causes inaccuracies in estimating this integral, and therefore, one specific reconciliation is one specific method in order to get over circumvent this problem is basically to use approximate long tails. If long tail is observed, approximate long tail with exponential decay. So, assume that the long tail is exponentially decaying, and so now there is it's an analytical function and it can be used to find out the integral c of t dt to a reasonable accuracy. So, therefore, if there is long tail, then it can lead to all kinds of numerical issues in order to estimate the RTD.